Okay, our second part of notes for reviewing for trig, we're going to look at trig graphs and trig equations. So if you remember a trig equation, what we're trying to do for the graph is we're essentially trying to graph things like f of x equals sine x, f of x equals cosine x are the big two, but then also tangent and those kind of graphs as well. So a couple things that we remember. The input is the x of these functions, but those inputs are actually angles. So we're going to put angles in. So I might do things like, what is f of pi over 4? Well, that's asking what's the sine of pi over 4. So from the unit circle, I know that's radical 2 over 2. But in general, the domain and range of these graphs are all real numbers. So I can plug any angle in I want. So when you plug these in, and if you think of our unit circle, so our unit circle kind of goes around, goes from 1, 0, and that goes all the way around. The biggest value for sine or cosine is always going to be 1, and the smallest is always going to be -1. And then every other number is in between those two. So we say the range is between -1 and 1. And you remember the graph, it kind of goes up and down, it just kind of bounces between those two numbers. And then once it does a cycle, it always repeats itself. Because if we think about the values, we have these angles that give us a bunch of different trig values for sine or cosine. Well, then we'll have another set of angles that have the exact same sine or cosine values. So it has this cyclical property, but will repeat every so often. So the way we typically will say that is we could say that the cosine and sine repeat every 2 pi n or 2k pi, depending on how you want to say it. So you could say the sine of some angle plus 2 pi is the same as the sine function. So this nature where it repeats itself is what makes them called periodic functions. So the graphs, hopefully you recall what the graphs of sine and cosine look like. So here's a table I made where I just plugged in some of our nice angles that we've heard of before. So these are all nice angles off the unit circle. So here are the two graphs essentially. And what you notice on these graphs is on the x-axis, I'm putting the different angles. So these are my angles that I picked. So I'm starting from 0 and I'm going all the way to 2 pi. And then we know that the pattern will repeat itself. So for sine, it goes up to its maximum of 1, down to its minimum of -1, and back up. And then, of course, it will repeat because they are periodic functions. Cosine, the difference is it starts up at 1, goes all the way down to -1 and back up. And then, of course, repeats itself. But the big thing is sine starts at 0, while cosine will start at its maximum, unless it's flipped, and then it would start at its minimum. So a couple of key features of graphs are typically what we call the amplitude and the period. So the amplitude essentially is how high and how low the graph goes. Typically it is 1. If you notice this first graph, we have an amplitude of 1 because it only goes up from 1 to -1. But if you multiply a sine or cosine function by a number, so if you put a number like 2 out here, you increase the amplitude to 2, which makes it go up to 2 and down to -2. You can also have an amplitude of 1/2, which will shrink it, makes it only go up to 1/2 and down to -1/2. Finally, you can have -2. -2 not only increases the amplitude, but it flips it, because a negative in front of a function will flip it. So instead of a cosine 2x would look like this. So this blue graph is y equals 2 cosine x. So the negative flips it over. It's going to flip it over on the other side. So amplitude is always positive, but that negative, what it really does is doing your flipping. So the amplitude of this one is 2, and the amplitude of this one is 2 as well. It's just that negative sign makes it flip over. So the second big thing is the period. So the period is how often it takes the graph to repeat itself. So in general, like we saw before, a general sine or cosine graph has a period of 2 pi. But if you change the number in front of x in a sine function, so if we say sine bx, this b value can actually change the period. And if you recall the formula, the period is just changed by dividing 2 pi by b. So if you have a function like this one, the period is simply going to be 2 pi divided by b. So if b is a whole number, it's going to make the period smaller. If b is a fraction, it's going to make it wider. So let's look at an example how we can graph some of these. So this one I'm going to try to sketch by hand, and of course I could graph it on Desmos and see what it looks like. So if I'm graphing this, I know the amplitude is 2, because that's the number in front. It is not flipped, and the period is going to be 2 pi divided by 1/4. Now remember, when you're dividing by a fraction, you're going to flip and multiply. So it's 2 pi times 4/1, which is 8 pi. So what I'm going to do now is I'm going to try to mark this off on my graph to try to make it look somewhat natural. So here is 0, and so this graph isn't going to repeat until 8 pi. Well, unfortunately, this graph does not go out to 8 pi, so I'm going to have to extend my graph a little bit. So we'll say this is 6 pi, and we'll say this is 7 pi, and we'll say over here is 8 pi. So the middle of this graph, since the whole thing is 8 pi, the middle is going to be 4 pi. So this is the middle point here. And then if I divide from 0 to 4 pi in half, I get 2 pi. And if I do the middle of those two, I get 6 pi. So here are my 5 key points. Now for sine, I'm going to start in the middle, because sine always starts in the middle. And then the next key point, which is now at 2 pi, is going to be there. And then back to the middle, down to the bottom, and you notice I'm going all the way up to 2, not just 1, and then back to 8 pi. So here is a sketch of my graph. And again, it will repeat itself because it is a periodic function. But again, I just try to figure out the whole distance, and then I just start cutting things in half. So I cut the whole thing in half, and then I cut the halves in halves to get these kind of major points where the graph is going to change. So let's look at another one. So this one is -8 cosine 10x, so a couple things. So the amplitude is 8, but it is flipped. And again, it's flipped because of that negative sign, but the amplitude is still a positive number. So the period is the other interesting thing in this one. So we're going to have 2 pi over 10, which is going to simplify to pi over 5, so a lot smaller. So if I look at my graph, here is 8, so kind of here is 8 up here, and here is -8 down here. So I'm just going to kind of put these lines to mark that out. Pi over 5 is here, and so then halfway between 0 and pi over 5 would be pi over 10, and then half of that is pi over 20, and half of that is 3 pi over 20. You literally could also count the boxes. If you count the total number of spaces between your beginning and end, you can divide that in half and then figure out how far you have to go for each of these marks. So here is the setup. Now it's cosine, so we're going to start at the top, unless it's flipped, which it is in this case, so I'll start at the bottom. And then I'll go here, back to the top, back to the middle, down here. And again, I would encourage you to look on your Desmos to see, is this actually the x-intercepts? Is this the minimum? Is this the maximum? All this should work out if you graph it on your calculator. But you'll notice this didn't take very long, and it's really nice when you're doing problems to be able to visualize the graph and give a quick sketch of it when you're doing problems. So the other things you can do is you can also move these graphs up and down. So when we move it left and right, we call it a phase shift or a translation. So in general, if you have an equation, a sine bx plus c or a cosine bx plus c, the phase shift is always going to be the opposite of c over b. So that's how we'll always find our phase shift. And again, what it really does is it figures out where we're going to start our graph versus 0. It might start at the right or the left of 0. So for this example, we have an amplitude of 0.25, We have a period of just 2 pi because there's no number in front of x, so that doesn't change because this number in front of x would change the period. But it has a phase shift because it has a c. So our phase shift is going to be negative pi over 4 because it's negative c over b, and c is pi over 4 divided by 1, so it's negative pi over 4. Now what that does is that means I will start my graph at negative pi over 4, which is over here. Did not make the best axis for this. So we'll say this is negative pi over 4. So now the end, the period is still 2 pi, so the end isn't at 2 pi because we don't start at 0. So the end of this graph is going to be at negative pi over 4 plus 2 pi. And again, we can add fractions. This is negative pi over 4 plus 8 pi over 4 if I get common denominators, which is 7 pi over 4. So 7 pi over 4 is the ending here. Now, as far as the middle, so you can think about it, we have 1, 2, 3, 4, 5, 6, 7, 8 full spaces between negative pi over 4 and 7 pi over 4. So if we go 4, 1, 2, 3, 4, this should be my middle. And then if I go 2 spots there and 2 spots there, those are my other key points. Now 0.25 is somewhere around here because this is 0.5 and 1, so somewhere like there. And it's cosine, so it's going to start, this is 0.25, I did 0.75 down there. So if you look at this, it's cosine, so it's going to start at its maximum unless it's flipped, which it's not. So it's going to start up here. And then down to my next point, to my next point, to my next point, to my next point. So it looks something like this. So between those two values, and this just shifted over a little bit. So it doesn't really start on the y-axis like a normal sine or cosine. It started at that negative pi over 4 and 0.25. So the final thing I want to look at in trig is when we are solving trig equations. Now, most of the time we're going to use our unit circle here. But the big idea is if you're solving a trig equation, somehow you want to get a trig value by itself. So if we do a really, really simple one, if I say, where is the sine of theta equal 1? Well, then I'm looking on my unit circle, where is sine 1? Well, if I think about my unit circle, sine is the y value. So this point up here has a y value of 1, and that's it. Because down here is 0, negative 1. Here has an x of 1. Here has an x of negative 1. So the only point is up here that has a sine of 1. And the angle at that point is pi over 2. So the solution to this equation is pi over 2. Now, other ones are a little trickier. If you look at this first example that I've solved, we're solving radical 3 cosecant x minus 2. But again, the first thing you want to do, and you notice it says solve on the interval 0 to 2 pi. Remember, that just means you're basically solving it on your general unit circle because all those angles will repeat, but we're just going to solve it on that interval. So we solve for cosecant. We get the cosecant by itself here. So here is where you're trying to find where is cosecant equal to negative 2 radical 3. Well, what we truly try to focus on is we try to focus on sine, because sine is the y value, or cosine, which is the x. So knowing that cosecant is negative 2 over radical 3, remember its reciprocal is sine, so that's the same as looking of sine equal to negative radical 3 over 2. This is an analogous case. If I had something like secant x equal 2, that's the same for looking at cosine x equal to 1/2. So if you ever have this other special trig functions, you can always take it back to sine or cosine or tangent. So essentially, in this problem, we were trying to find where sine of x equals negative radical 3 over 2. Well, that's the y-coordinate, so on my unit circle. So if you pull your unit circle out and you look on there, which one has y-coordinates of negative radical 3 over 2? It's exactly at these two angles. It's at 4 pi over 3 and 5 pi over 3. So those are my two answers. Now, there are definitely other ones, because think about this. I could go here for this angle, but I could also go all the way around. But that's out of my interval. But there are infinitely many solutions, essentially. We just are looking at the ones between 0 and pi, or 2 pi, pardon me. All right, let's look at these equations. So we're trying to solve these on the interval 0 to 2 pi. So again, first thing you have to do is get the trig function by itself. So in this case, not too terrible. So we get 2 cosine theta equals negative radical 3. I'll divide by 2. So I'm looking, where on the unit circle is cosine equal to negative radical 3 over 2? Now again, this is the x-coordinate because cosine is always the x-coordinate. So on my unit circle, I'm looking for where those points are. Well, I see here, I get radical 3 over 2, comma 1/2, but that's not right because I want it to be negative. If I look over here at this point, I get negative radical 3 over 2, comma half. So that one is good. And that is 5 pi over 6 on your unit circle, I believe. Down here, I have negative radical 3 over 2, negative half. So that's good because the x-coordinate's what I'm looking for. So that's 7 pi over 6. If I look over here at 11 pi over 6, I get radical 3 over 2, comma negative half. That's not good because we want negative radical 3 over 2. The two spots where it seems to be good is going to be 5 pi over 6 and 7 pi over 6. Now, are there other spots? For sure. But the only ones between 0 and 2 pi are those values. All right, finally, let's look at this one. This is a trigonometric quadratic function where you have a sine squared and a sine and a number. So this is, if you look at it, it's really a quadratic function. Because if I think of this as something squared, let's think of it as y squared. It's sine squared, so we'll call it y squared. So if I think of this, this is like 3y minus 4 equals 0. So really, it does look like a quadratic that you can solve by factoring and such, but instead of y or x or some variable, it has these sine x's. So a way to solve these is I'm going to replace it with this variable. So essentially, I've taken sine theta, and I've replaced it with y, and now I'm going to factor that. So we get y minus 4, and then y plus 1. And then I'll just solve that. So y equals 4 and y equals negative 1. But we're not trying to solve for that. We're trying to solve for sine. So I'll now plug that back in. So we get sine theta equals 4, sine theta equals negative 1. Now, as far as sine equals 4, if I look for the y-coordinate on the unit circle, remember, the biggest it gets is 1 and the smallest is negative 1. So this has no solutions. If you ever have sine or cosine equal to a number bigger than 1 or smaller than negative 1, it's no solution. Now, as far as sine of theta equal negative 1, the only place that happens is down here on my unit circle, because again, we're looking for the y-coordinate. And so that should be at theta equal 3 pi over 2. So that's the only place between 0 and 2 pi that this quadratic equation would work. So hopefully this is not too bad. Obviously, if you have questions, let me know. The next review section will be on exponentials and logs, and that will be the end of our kind of review part.